On June 21, 1948, a machine completed 3.5 million calculations and arrived at a correct mathematical answer. To do this, it ran a program, entirely from its own internal memory. No other machine had ever accomplished this. The Small-Scale Experimental Machine, or SSEM, stretched 5.2 meters across a room. It weighed nearly a ton and drew 3,500 watts of continuous power. Achieving this logic required high hardware density, relying on hundreds of fragile vacuum tubes to process and hold electrical signals. This breakthrough took place at the Victoria University of Manchester. In the immediate post-war period, the university became a center for researchers applying wartime radar expertise to civilian science. During that single 52-minute run, computation transitioned from a physical process into an electronically programmable one. Visitors to technology museums frequently ask to see the first computer. But among historians, first is practically a taboo word, because the answer always depends on how you define the machine. To declare a winner, you have to pile on specific adjectives. You have to specify if you mean the first automatic, digital, binary, or general-purpose machine. To navigate these claims, scholars use three technical benchmarks: evaluating a machine's hardware design, its logical architecture, and the complexity of its code. We'll use these standards to judge if the Manchester baby originated modern computing or was just a hardware testbed. Distinguishing between physical capability and the logic of modern code is the only way to accurately identify where the digital age truly began. By the late 1940s, processing speed had already reached incredible levels. The limiting factor was no longer the speed of the calculation, but the speed of memory access. This image of the ENIAC shows how machines were controlled before internal memory. Technicians were tasked with manually plugging in cables and turning dials to set up specific mathematical routing. Configuring a machine for a single new equation could take several days. This manual setup time effectively neutralized the machine's electronic calculation speed. The engineering challenge was to find a way to electronically trap, hold, and retrieve a digital 1 or 0. To maintain speed, this memory system could not rely on slow, physical moving parts. A purely electronic, high-speed memory system would finally allow the computer to calculate as fast as its electronics permitted. Engineers Freddie Williams and Tom Kilburn developed a solution by repurposing surplus radar technology from the war. Their invention centered on the cathode-ray tube, or CRT, which was commonly used to display signals on oscillographs like this one. This diagram shows the internal physics. An electron beam fires at a phosphorus screen. When it hits, it leaves a localized electrostatic charge, which the machine can interpret as a digital 1. The major problem was that this charge is ephemeral. Without intervention, the data fades away into the screen in roughly 0.2 seconds. Williams and Kilburn devised a continuous loop to solve this. The system rapidly reads the fading charge and immediately rewrites it, keeping the data alive. This continuous refresh cycle is the exact principle that modern dynamic RAM, or DRAM, still uses in every modern laptop and smartphone. The SSEM was never intended to be a full computer. It was built as a minimal testbed to prove the Williams-Kilburn memory tubes functioned. Because it was a proof of concept, its specifications were modest. It used a 32-bit word length and only 32 total words of memory, with hardware capable of only 2 native functions, subtraction and negation. This grid represents the historic 17-instruction program written by Tom Kilburn. To find the highest proper factor of 2 to the 18th power, the machine performed a massive sequence of brute force subtraction loops. By running directly from memory, the machine satisfied the first benchmark, the EDVAC hardware paradigm. It also satisfied the second. Routing transfers through a central unit and storing instructions and data together fulfilled the von Neumann architecture. Structurally and architecturally, the testbed was a success. It provided the mechanism to move computing from fixed-wire calculators to stored program machines. The final historical standard is the modern code paradigm. This requires the execution of complex sequences, arbitrary logic jumps, and addresses that change during the program's run. Historians point out that Kilburn's 17-line code was a hardware test. It lacked the logical complexity that many scholars require to qualify as true software. This rigorous standard introduces a rival for the title, the ENIAC, following a massive conversion completed in 1948. This split screen compares the logical flow. While the baby ran a single loop, the converted ENIAC executed a complex Monte Carlo simulation for nuclear fission. That program utilized the world's first closed subroutines. Retroactive labels are difficult because the word software did not exist in the 1940s. Categorizing one program as software and another as a hardware test is a subjective judgment. If we define the first computer by rewritable memory and hardware architecture, the Manchester baby wins. If we define it by the complexity of the code executing, the converted ENIAC takes the crown. The debate over which machine was first often distracts from the project's actual impact on the global computing industry. Led by mathematicians Max Newman and Patrick Blackett, the testbed immediately evolved into the Manchester Mark I. This was commercialized as the Ferranti Mark I, the world's first general-purpose computer available for purchase. The success of the machine attracted brilliant minds like Alan Turing to Manchester, which accelerated the field of artificial intelligence. The Manchester project was the essential spark. It moved computing out of military secrecy and into a commercial and industrial reality. Identifying a single inventor, or a first computer, is a simplified version of history. This image of Babbage's mechanical gears grounds the true lineage. Charles Babbage conceived the architecture. Alan Turing theorized it mathematically. Williams and Kilburn built the physical memory, and the ENIAC team evolved the code. The original Manchester baby was dismantled for parts. Today, a working replica built with vintage components still operates, bridging a 75-year digital gap. The greatest legacy of the Manchester baby isn't a disputed title on a timeline. It is the design for memory that billions of modern devices still rely on every single second.